Okay, so sorry for this. So this is hybridization. We just discussed the ethane molecule with sp3 hybridization on both sides. Now let's do the same with a different molecule. Let's take, let's, all right, here this is ethane, so it's C2H6. And now let's have a look at this molecule, C2H4. So again, we have two carbon atoms, one here and one here. And we have now only 4 hydrogen atoms. So what's your guess for the type of hybridization on each of these carbon atoms? Can anybody write it probably in the chat? So we had sp, sp2 or sp3. What's the case here for the ethene molecule? sp2, exactly, sp2. Now what does sp2 indicate? It indicates that we have one s, the 2s orbital, so as one ingredient an s orbital, and we take 2 of the 3 possible p or pi orbitals. We take, to stay in the xy plane, we take px and py. Now we make the linear combination of px, py, and the s to form the orbitals, and you can see they will look like this. One here, and one here. So 1, 2, 3. I always have a lobe that goes in one direction, reaches out in one direction, and in the opposite direction it's very short. This is the linear combination of the S with the pi. So one lobe gets enlarged, the other one gets reduced. And since I have px and py, I can form these 3 lobes. And what's important to know is that in sp2, they are forming a plane because I have 3 lobes. 3 lobes, by definition, they are lying in the same plane because I'm just using px and py orbitals. So I can only end up with the linear space in 2 dimensions, xy plane in my description. And I'm doing the same now on the other side for this second carbon atom. So it looks like this, 1, 2, 3. And again, I'm forming here a bond, CC, because I have overlapping sp2 hybrid orbitals. This is my first molecular bond formed here. And with the 2 other lobes, I can bind the hydrogens. So this is again a combination here of the 1s of the hydrogen with this sp2 hybrid orbital of the carbon. So this gives me a molecular bond. This is one, this is one, this is one. All of them have the same structure, namely a sp, in this case sp2 orbital, overlapping with an s orbital, which has this rotational symmetry. Therefore, all bonds that I've drawn here are sigma type bonds. Now, this molecule is not happy yet because there is some part missing. If you count the electrons, you'll see that we're missing out on some electrons here. We have another bond. Namely, we have chosen sp2 hybridization in the xy plane to show this on the board with xy lying like this. And it means we still have one orbital which is not in a linear combination. It's the p z orbital. And the p z orbital in our coordinate system is standing. So we look at it in projection, and the p orbital in projection will look like this. Right? So this is our coordinate system x and y. Now we look at the system from the side. So I have x and here z. Then the molecule would be in plane. So this would be C. This would be H, C, and here would be H. And the orbitals that we have drawn here in orange look from the side like this. And here you can see this is the other type of overlap. Here we have an overlap of pi orbitals. So they are a bit more diffuse and are overlapping. and are forming the second bond. So this tells us that the structure in this case is CC with this double bond, a sigma type bond between the sp2 hybrids and a pi interaction, with pi overlap. This is a pi type bond between them, and then we have the sigma bonds with the hydrogen atoms. So this is an example of the sp2 hybridization. And the last type of hybridization is something I will discuss with you on a molecule which I have not ready. I'll build it quickly for you. All right, oh, there we go. Okay. The next molecule is CO2. And my question for you is, if you look at CO2, what kind of hybridization would you expect on the carbon and on the oxygen? So think about it. I'll erase blackboard. Has anybody written something? So what's on the carbon atom? What's your guess? What kind of hybridization can you find on the carbon atom? I give you a hint. CO2 is a linear molecule. So again, we introduce our coordinate system x and y, and we have the atoms oxygen, carbon, oxygen. That's how it looks. It's linear. sp2, I asked for carbon, I think. Carbon is not sp2, but the oxygens are sp2. So we have one hybridization correctly identified. On oxygen, it's sp2. Why? We will see in a minute. But on carbon, it is, since it's linear, it is sp. You will see why in a minute. Here, on the carbon atom, we form our molecular bonds in two directions. So what the linear combination, or how the most convenient linear combination, is a combination of an s orbital, the 2s of the carbon, with the px orbital. So you form an sp hybrid orbital. You take the s and the p in x direction, so this gives you one lobe looking like this, and the other one looking like this. On sp. Now, that means in our set of atomic orbitals, of valence atomic orbitals, we have used up one s, so the 2p, the 2s orbital, so one of s type, and we have used one of the pi orbitals, the pi x, meaning the pi y and the p z are still available. Okay, now what are we doing on the oxygen side? On the oxygen side, we said it's sp2. It forms a linear combination of px, py, and the 2s orbital, looking like this. 1, 2, 3. And the same on the other side. First lobe, second, and third. So we see this is an sp2 with sp overlap, forming a sigma type bond here. Same here. Is the first bond a carbon-oxygen bond and an oxygen-carbon bond. Now, what else do we have? We have electrons in the system that still have to go into some bond. Now, what we haven't touched yet are the p, y, and the pz orbitals here. I'm using, say, orange for the py. The py here looks like this. And the pz in our system looks like this. Now, here on this side, we have used px and py to form, together with the 2s, the sp2 hybrid, meaning that the pz orbital is still unused and can form our p-type bonding, a pi bond, which we have to identify by looking again from the side. Okay, so here it would look like this and this. And you see you have this type. If I blow this up a little bit, make it a bit more diffuse, you can see you have an overlap between the pi orbitals here and here. And here on this side, we have to cheat a little bit. We said we form an sp2 here, but we won't form it from x and y. We will form it from z and x, for example. So you think of this a little bit twisted, so that we have the py orbital overlap with the py orbital here that is free. So on this side, we made an sp2 hybrid with px and pz, leaving the py as untouched p-type orbital, and we have a pi bond here, looking, when I look in the xz plane, like this, projected. Okay, so this means the overall molecule has a bond here, sigma, a bond here, pi, a bond here, sigma, a bond here, pi. So this gives us a double bond, and we can combine this with our knowledge from school chemistry. It means OCO, and it also tells us, in order to get the remaining electrons, because if you count electrons, you will see that we also have electrons that have to be situated in an orbital which does not contribute to bonding. We will have 2 electrons in this and 2 electrons here and on the other side. So you can also indicate the non-bonding W-occupied orbitals by this dash notation, and you end up with this structure for the CO2 molecule. And now I show you how this molecule looks like in the model. It's pretty fancy. The idea is that they drill the holes into the carbon atom in this tetrahedral arrangement, so you can easily model the single sigma type bond. But if you want to go to a double bond, you have to use a connection that is a little bit flexible, because here you have to bend then, if you make these holes according to the hybridization idea, into carbon and oxygen this way. But you can, by deforming them a little bit, also end up with the correct picture, you see we have to form a bond here, and normal or orthogonal to these two, the other bond situation. So this is also somehow overlap, or is giving an idea of how the hybridization is really realized in the molecule by having an sp combination here and here, using different types of pi orbitals on the oxygen left and on the oxygen right. So this is a very convenient way of playing with molecular structures based on molecular orbital theory and molecular symmetry, right? So you see, just by taking symmetry into consideration and looking at which type of orbitals you have accessible in each molecule, you can already derive structural information about the molecule. And you can also see where certain where certain electrons have to go, which are not participating in the bonding itself. So they are sitting here and here, and you can see each of them fulfills this so-called octet rule, as you learned it from school, at school, where we say that each of the atoms would like to arrange itself in the molecule in a way where it has this noble gas or rare gas configuration, being surrounded by 8 electrons. So to have this shell completely filled, 2, 4, 6, 8 here, and the same for each of these atoms in the molecule. So this is about hybridization, and I'll stop here. The idea was to show you symmetry and knowing which orbitals are interesting for forming a molecular bond. It's always the valence orbitals, so the orbitals that are occupied but highest in energy. They will tell you already how the molecule will be shaped. Okay, I'll stop here and